Okay, so in today's lesson, we're actually going to look at the properties of a Poisson distribution. With every distribution, two important properties that we like to work with, to know, and potentially to investigate, manipulate, explore are going to be the mean and the variance. So, the mean and the variance of the Poisson distribution. We already know that the parameter that we use for the Poisson distribution is lambda. Now, lambda is the average number of events that would occur within a given time interval, or the rate at which these events occur. So, if we were then asked what we would expect to happen, what would be our expected value within a Poisson distribution, well, the expected value is that lambda. That's the rate that we know happens. That's the rate that we expect to happen. The most likely, the most popular outcome is that we see lambda. So if we knew that on average 5 cars pass a school every minute, well, any given 1 minute interval, we would expect to see 5 cars. We know sometimes it will be less and sometimes it will be more, but that's the most likely outcome to happen. Interestingly enough, and there's a proof for this, I might put it up at the end of the video, variance of x also equals lambda. So both the expectation and the variance are the same value. Now, the fact that we're expecting them to be the same value to appropriately model as a Poisson distribution lets us use that as a consideration in the first place as to whether or not the Poisson distribution is a good model. So sometimes you'll be asked to calculate the mean and the variance. If they're similar, you can start to think a Poisson distribution might be appropriate. If they're far apart, then you can start to think a Poisson distribution will not be appropriate. Let's just run through an example so you can see that in action. So here we're told that a botanist counts the number of daisies, we're going to use X to represent the daisies, in each of 80 randomly selected squares within a field. And here are the results, the summary stats. Sum of X equals 295. Sum of X squared, 1,386. And we can say that N is going to be 80. In part A, we've been asked to calculate the mean and the variance of the number of daisies per square for the 80 squares, given our answer to 2 decimal places. Well, this is now just a straight maths question. This is, do you know the formula for the mean and the variance? Can you get us an answer? We'll start with X bar. So X bar is the sum of X over N, 295 over 80, just into your calculator, and we get an answer of 3.688. The question actually asks for 2 decimal places, so 3.69 we should actually write here. Sigma squared, well, the formula is sum of X squared over N minus the sum of X over N squared. Be careful that you're not using the standard deviation formula, but you are using the variance formula. Substituting the values in, so 1,386 over 80, subtract 295 over 80 squared. Okay, all of that into your calculator, and we'll get a variance of 3.7273. Part B actually asks us to explain how those answers support a choice of the Poisson distribution as a model. Well, let's look at the numbers. They are quite close. What level of accuracy would they be correct to? Well, to 2 decimal places, they're not the same. We've got 0.69 and 0.73. But to 1 decimal place, they would actually be the same number. It would be 3.7 and 3.7. And obviously to the nearest whole number, they would both be 4. But we want to go for the most accurate we can be. So to 1 decimal place, these are both 3.7. That supports the Poisson distribution because we expect in the Poisson model for the mean and the standard deviation to be approximately equal to each other. Part C now wants us to use a suitable value of lambda to estimate the probability that exactly 3 daisies will be found in a randomly selected square. Well, like we said, it's 3.7 to 1 decimal place, so we'll use that. We'll use that as our suitable value. and we'll just mark out the distribution. So x is going to follow a Poisson of 3.7 per square. That's how many daisies we expect per square. Now the probability we see exactly 3. It's a little bit less than the expectation, with 3 being one of the integers that's closest to the expectation. It's going to be one of the highest probabilities. So either probability x equals 3 or the probability x equals 4 will be the highest probability for any individual outcome for this Poisson distribution. Let's find the probability x equals 3. So, just writing this out as usual, we can either use the probability function, e to the negative lambda, lambda to the x over x factorial, or we can use our calculator function, PCD 3.7. Either of them, both of them, get us the answer 0.2087. So 21%. It's quite a high percentage for just one individual outcome. Okay, so this is us using the knowledge we have about the mean and the variance and the proximity we expect them to have to each other for us to further make a decision about whether the Poisson distribution is a suitable model to choose. Okay, so just be on the lookout for questions like this. You do need to write an explanation, and that explanation does need to be sound and in context. Okay, so I'll let you get some practice, and now that we've thought about the properties of the Poisson distribution, we'll go back to our first distribution, which was the binomial, and we'll make sure that we're comfortable with the properties there. The expectation we already found. We're also going to find the variance. The reason we go back and look at the binomial is because there is a special relationship between the binomial and the Poisson. And if the conditions are just right, we can approximate a binomial distribution into a Poisson distribution. So we'll see how that all works in the next few lessons.